In this short video, we're going to take another look at plotting vector fields. Do you remember in chapter 1.2 we did some plotting of vector fields, and in particular we plotted the electric field, which was the gradient. We didn't use the word gradient at that time, but it was the gradient of the electric potential, and you can look at that now and see that it is the gradient, since the x-coordinate is the gradient of the electric potential with respect to x, and the y-coordinate is the electric potential partial derivative with respect to y. And what we did is we said we were going to draw this electric field because this is a sort of a complicated expression to graph, but we were going to construct lines which were tangent. And to do the tangent, we calculated the slope, or rise over run, and we used the electric field partial derivatives, and we got this equation here. We integrated this because this is a differential equation, which could be made exact by using this as an integrating factor. And it was quite a bit of calculation to get there, but we saw that then these electric fields were essentially circles. There are two motivations to take another look at plotting vector fields. The first one is here. Not every vector field has an associated potential field. That is, not every vector field is the gradient of a scalar field. And here, we took advantage of the fact that the electric field is the gradient of the electric potential. But when we talked about Stokes, we had seen this other theorem that said that if the curl of A is equal to 0, then A is equal to the gradient of a scalar field. And it also turns out that if A is the gradient of a scalar field, then the curl of A is equal to 0. So these two things are equivalent. And as we know, not every vector field has a curl of 0, and therefore not every vector field has an associated potential field, or not every vector field is the gradient of a scalar field. So we can't use this technique on every vector field. Second, more importantly, or just as important, is here the electric potentials, they were difficult to graph, which is why we went through this other route, which was also kind of difficult, but in the end we got something that we could graph. However, there are many vector fields that have much easier functions, and it would be easier to graph directly. And that is exactly what we're going to look at in this next example. I have given you this example before, but we'll take a quick look at it before we get to our main example, and that is a vector field on Rn is a map that assigns to each point x in its domain a vector f of x. And graphically, we may picture f as attaching an arrow to each point. So in other words, if we have a vector field that assigns to the point 1, 2 the vector 4, 3, that means over here at the point 1, 2, because this is f of 1, 2, we're going to move this vector, which is the vector 4, 3, so that it starts over here at 1, 2. Remember, the thing about vectors, they have magnitude and direction. They are not stuck to the origin. We often start by drawing them at the origin because then we can get the 4, 3, the direction just right. But you could actually start anywhere and go over 4 and up 3, or up 3, and you could draw the vectors. So the vectors can move around. The example I will do is of rotary motion, such as the motion of particles on a record player, and it's described by the vector field v of xy equals minus yx. And here I have some of the points where I plug in xy into v of xy, and I chose small points, 1, 0, negative 1, 0, 0, 1, 0, minus 1, 1, 1, just to start. And what v does, to get its x-coordinate, it takes the y-coordinate and puts a negative, and then to get the y-coordinate, it just brings over x. So here, to get the x-coordinate, we just take the y-coordinate, make it negative, but it's 0, so it just stays 0, and then we bring over the x. Here again, the 0 stays 0, we bring over the x. Here, something sort of interesting happens. We bring over this and make it negative, so we have a minus 1, we bring over the x. Again, we take the minus 1, make it negative, so we get positive 1, bring over the x, and then for 1, 1, for y, we bring it over to x, make it negative, and then x just becomes y. So these are the first points I'm going to graph. At the point 1, 0, that's this point here, x equals 1, y equals 0, I'm going to put the vector that is 1 unit length pointing in the positive y direction. That's this vector here. So I'm going to move this over to 1, 0. Next, at the point -1, 0, that's this point here, x equals -1, y equals 0, I'm going to put the vector 0, -1. That's x equals 0, y is equal to -1. So I need to move this vector over to my point. Next, at the point 0, 1, that's x equals 0, y equals 1, that's this point here, I'm going to have the vector that points in the negative x direction. It's a unit length vector in the negative x direction, so I'll move that to my point. And this next one I'll just do, so at the point x equals 0, y equals -1, that's this point here. I want to point that vector that points, a unit vector that points in the x direction, the positive x direction. So it'll look like this. And then finally on this table at the point 1, 1, that's x equals 1, y equals 1, I need the vector -1, 1. So -1 in the x direction, +1 in the y direction. It's this blue vector here that I need to move over to the point 1, 1. So now I have little pieces of vector fields, but I don't have any curves that connect except for these two here. So I'm going to start choosing my points so that each consecutive points is at the end of my last vector, and that way I can kind of get a continuous curve. So for this one, since this is a little bit of a curve, or the start of a curve, the next point I'm going to choose to plug into my vector field is the point x equals 0, y equals 2. And when I plug that in, I get -2, 0, which is this vector here, right? Oops, sorry, that shouldn't move. I have a vector that's -2 in the x direction, 0 in the y direction, and I want to move that to the end of my last vector. That makes the next point that I want to look at is this point here, which is the point -2, 2, and when I plug that into y, I'm going to get -2, -2. Here I have my vector -2, -2, and I want to move it so that it starts at the end of my last vector. I can start maybe over here and see if I can get more of a path. So the ending point here is that x equals -1, y is +1. When I plug that into my vector field, I'm going to get -1, -1. So that -1, -1, I'm just going to sort of trace it with my light pen, right, is this angle that goes 45 degrees. So I'm just going to draw that directly in here. So my next starting point is going to be x equals -2, y equals 0. Plugging this in, I'm going to get 0, -2. So 0, -2, 0 in the x direction, -2 in the y direction. So it just points straight down 2 units. And then I'm at the point -2, -2, and my v of -2, -2 is 2, -2. So if I kind of do this with my pen, so if I'm over here at 2, -2, so I have this 45-degree angle, it'll go this way. So you can see here you have the start of rotary motion, here you also have the start of rotary motion. And if you continue plotting these points, these vectors, this is what you would get, something like this. And that's it for this video. Thank you for watching.